The last talk before the break will be given by Komal Negi from the Indian Institute of Technology from Ropar. You can start.
Thank you. Okay, good afternoon, everyone. First of all, I want to thank the organizer of this conference for bringing us all together. My name is Komal Negi. I'm a research scholar at IIT Roper Department of Mathematics. Today, I'll be discussing Twisted Virtual Braid Group, which is a joint work with VG Bardakov, T.A. Kozlovskaya, and M. Prabhakar. So this is the overview of today's content. I'll start with the definition of twisted knots and links, twisted virtual braids. Then we'll see how we have defined twisted virtual braid group. Then we'll explore some of its subgroup and decomposition of its group. So let's begin with an introduction. So twisted knot theory was defined by M.O. Borguin in 2006, which is actually a generalization of virtual knot theory, which was discovered by Louis Kaufman in 1999. So let's see how twisted knots are defined. Twisted links corresponds to a stable equivalence classes of links in oriented 3 manifolds, which are orientation I bundles over closed but not necessarily orientable surfaces. Uh, Let us understand by an example first. So this figure shows a 1-point knot in a thickened Klein bottle on the left hand side, where this thickened Klein bottle is shown as a cube with identification of its sides. This blue one is identified with the blue one, and the red one is identified with the red one. And the diagram of one foil knot on the right hand side, this has odd number of bars on its edges. So these paths which passes through odd number of bars are actually orientation reversing in projection of the link in the embedded Klein bottle. So we generally used to study knots and links through their diagrams. Similarly, we will study the twisted links by their diagrams only. So this is one of the example of twisted link diagram. So twisted links are diagrammatically defined as twisted link diagrams modulo isotropy R2 and local moves called extended Rieder-Master move. So these are the moves. So here you can see this R1, R2, R3 are the classical Rieder-Master moves. Then if you will add V1, V2, V3, V4, then these will be virtual Rieder-Master moves. And if you will add this twisted moves T1, T2, T3, then this will forms twisted Rieder-Master move, or we can say extended Rieder-Master moves. So as we know, there is a nice connection between links and braids. Like in classical knot theory, the Alexander theorem says that given an arbitrary link, it is equivalent to a closure of a braid. A similar kind of connection exists between virtual links and virtual braids. Recently, we have discovered a similar connection between twisted links and twisted virtual braids on this work, Twisted Virtual Braids and Twisted Link, which is a collaborative work with M. Prabhakar and S. Kamata. So this Alexander theorem for twisted link says that every twisted link is represented by the closure of a twisted virtual braid diagram. So let's see how twisted virtual braid diagrams are defined. So these are the braid diagrams or braid diagrams of degree n with possibly with the virtual crossings and bars. By this example, I think it will be more clear. On the left hand side, this is a figure of virtual braid on N 5 strands. Here we have classical crossing as well as virtual crossing. On the other side, we have twisted virtual braid on 3 strands. This you can see we have classical crossing, virtual crossing as well as bars. Now for the equivalence between two twisted virtual braid diagram, we say these two, any two virtual braid diagrams, twisted virtual braid diagrams are equivalent if they are related by finite sequence of ambient isotopy and extended Rieder-Master moves, keeping the condition of twisted virtual braid diagram. So these are the braid moves corresponding to twisted virtual braid diagrams. Or we can also say this, that a twisted virtual braid is an equivalence class of twisted virtual braid diagrams. There is a nice property satisfied by these twisted virtual braids. The set of all twisted virtual braids with n strands forms a group, and that group is called twisted virtual braid group. We denoted it as TVBN, and it is generated by the standard generators, that is sigma I, rho I, and gamma I. So here you can see sigma and sigma inverse are the braids corresponding to the real crossings, and this rho I is corresponds to the virtual crossings, and gamma I corresponds to the bar. So these are the defining relations of this group. Now our problem is in which we are working on is to find the subgroups of this group such that we can write this group in terms of its subgroups. So one of the subgroup is twisted virtual pure braid group. So first let us see how we have constructed this subgroup. First we have considered a group Sn, which is a symmetric group generated by transpositions rho 1, rho 2 till rho n minus 1. And we define an epimorphism of TVBN onto Sn. So this epimorphism maps sigma I and rho I to rho I only, and gamma j's to identity. So kernel of this epimorphism will form a subgroup of this group TVBN, which we have denoted as TVPN, that is twisted virtual pure braid group. Now let us consider these type of elements, lambda ij, lambda ji's. These type of elements are the elements of the subgroups TVPN, and we have written these elements in terms of generator of TVBN. This is how these elements look like geometrically. Now the next question is, can we present this subgroup in terms of its generator and relations or not? So the answer is yes, we can write this subgroup in terms of generators and relations. So this is the presentation of this subgroup. So where the generators are lambda KL, where K is not equal to N, between 1 to N, and gamma J's, where J is between 1 to N. And these are the defining relations. So I'll discuss the idea of this group. For this presentation, we have used this Reidemeister-Schreed method, which says that if we have a group with presentation in terms of its generator and relation, and if we have a right cosine function for G modulo H, where H is one of its subgroup, then we can find the generators and relations of this subgroup by using the generators and relation of its group. Okay. So in our case, the group is TVBN and the subgroup H is TVPN, and the right cosine function or representative is Sn. And we have considered the same map from TVBN to Sn. For every element of TVBN, it will map to W bar, that will be an element of Sn. Okay, so this type of elements will form generators of TVPN. So these elements are lambda A dot lambda A inverse bar, where lambda belongs to Sn and A belongs to generator of TVBN. So in our case, we have three types of generators. So we have three types of possibilities for A, that is rho I, sigma I, and gamma I. For corresponding to rho I, we will get only identity element, and corresponding to sigma I, we will get lambda KL type of elements, and corresponding to gamma I, we will get gamma J type of elements. So it is clear that this subgroup will be generated by lambda KL type of elements and gamma J type of elements. So due to time constraint, I haven't included the formula for defining relations. So there exists a formula from which we can find the defining relation of its subgroup by using the defining relation of G in a similar manner. So now we have also proved that this TVBN is equal to a semi-direct product of TVPN and Sn. Next is, can we find decomposition of this subgroup TVPN? So if we define a epimorphism from TVPN to AN, where this lambda KL type of elements maps to identity and gamma J type of elements map to gamma J only, where AN is this subgroup. So this can be extended to endomorphism of TVPN, and we can prove that this subgroup AN has this type of presentation. This AN will be generated by gamma I types of elements, and these are the defining relation. Basically, this AN is isomorphic to Z2N. So if we denote this group kernel of psi p is equal to PLN, which is a subgroup of TVPN. So we can prove that TVPN is equal to semi-direct product of PLN and AN. Using the same method, Rydam-Axis tree method, we can prove this also, that PLN has this presentation. These are the generators of PLN, and these are the defining relation of this subgroup. In the same way, like we have worked for TVPN, we can find other subgroups of this group twisted virtual braid group. So we have considered the second type of epimorphism from TVBN to SM, where the sigma I maps to identity, rho I maps to rho I, and gamma J maps to identity. Again, the kernel of this map will be a subgroup of TVBN, and we denoted it as TVHN. So if we consider this type of elements Xij and Xji, which are actually the elements of TVHN only, and we have written these elements in terms of generators of TVBN. And this is how these generators look like geometrically. By using the same method, we can prove this presentation for TVHN also, that this group is generated by these type of element XKL and gamma J's, and these are the defining relation. Now we have two subgroups of TVBN. So the next question is, either these subgroups are isomorphic or not. So starting with the n equals to 2, these two subgroups, these are the presentation for TVP2 and TVH2 respectively, and these are isomorphic. So these subgroups are isomorphic to free product of Z and Z2 cross 2, Z2 cross Z2. But for n greater than equal to 3, these are not isomorphic. This we can prove by finding the abelianization, or we can prove this by showing that abelianization of these subgroups are different. So if abelianization of two groups are different, then these two groups can't be isomorphic. Now, if we change our map, we can construct other subgroups of TVBN also. Like here, we have defined two endomorphisms of TVBN by reaction on the generators. So first one is phi PT, where sigma I maps to rho I, and rho I maps to rho I, gamma J maps to gamma J. And second one, sigma I maps to identity, rho I maps to rho I, gamma J maps to gamma J, where this TSN is a subgroup of TVBN, and it is generated by these elements, rho I's and gamma J's. Now we can prove this, that the image of this map will be TSN only, and this will be a subgroup of TVBN, and it is isomorphic to extended symmetric group, and hence it has a presentation TSN equals to semi-direct product of AN and SN. Now I want to end my talk by giving an open problem. We all know that there exist in literature, there exist braid groups and virtual braid groups. And we know that braid group is a subgroup of virtual braid group. Now the next question is, that is virtual braid group is a subgroup of twisted virtual braid group or not? So these are my references for today's talk. Thank you for your attention.
Thank you. Are there any questions or comments? No questions and no comments. I wrote one. Can you please show the slide where you introduce this twisted virtual braid group?
This one.
Relations. Yeah, I see. So is it true that if we look to the subgroup generated by sigma 1, sigma 2, and so on, sigma n minus 1, then we will have a classical braid group as a subgroup of the twisted virtual braid group?
We can't say it directly because if we look at the proof of that braid group is a subgroup of virtual braid group, so it is not like that if we consider sigma is only and the relation that it will considering those relation, then it will form a subgroup.
I see. So there is a homomorphism from the braid group, but we don't know if it is faithful.
Yes.
Yeah. Yeah, I see. So it means that the same for the virtual braid group. And can you please go to the first slide where you introduce these guys? Yeah, just. So you say that twisted knot theory is generalization of virtual knot theory. What do you mean when you say that it is a generalization?
Generalization means in virtual knot theory, we are considering thickened surfaces where the surfaces are orientable. But in twisted knot theory, we are considering thickened surfaces where surfaces may not be orientable.
My question is that, like, if you have two twisted knot diagrams, sorry, two virtual knot diagrams, which are equivalent as twisted diagrams, are they equivalent as virtual diagrams?
Okay, no, that is not true. But in classical case, it is true. There is one paper by S. Kamada. So
Yeah, I see. Yeah,
in
that's why for me
in
it's
that
not really a
paper,
generalization.
okay, fine. But if we consider the surfaces corresponding to the surfaces, we can say it's a generalization. But your point is also correct. We can't say it is generalization. But when M.O. Borgwin defined this twisted knot theory, so he said that it's a generalization of virtual knot theory in that sense.
I see. Thank you. So let us thank the speaker again.